Thomas Jefferson National Accelerator Facility is a laboratory for basic nuclear physics research operated by the U.S. Department of Energy. At Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Well, good evening, ladies and gentlemen. My name is Dave Kausch. I'm the fire protection engineer here at Jefferson Lab. I'd like to welcome you to this evening's Science Series, where you will hopefully learn all the hidden worlds of technology. This evening's speaker is interesting fellow. He and I spent some time together. Did you all know that this is National Turn Your TV Off Week? And, you're here with your TVs off, so that's wonderful. Our speaker survived, can you believe it, for 12 years without a television. In 1997, he acquired a new television with some other things. He's also a tenured professor at the University of Illinois, and he's going to be conducting the presentation this evening. The gentleman's name is Bill Hammack. Thank you.
Thank you, Bill. Well, I'm here tonight actually as a tour guide. A tour guide to a hidden world that surrounds you, an invisible world that you rarely look at. In fact, it's a world that I have introduced people to for about 5 or 6 years now on public radio. I've done over 250 pieces for them talking about the hidden world of engineering. And all of those pieces, like tonight's talks, are aimed at people like you. They're aimed at people who enjoy learning something new, but aren't necessarily an expert in science or in engineering. And I hate to say this, but I'm going to start with the dullest thing imaginable. I'm going to go through the first 45 minutes of my day, and on the surface it's very mundane, but here's my claim, that the simple actions that you see, which are the things that all of you go through every day, are made possible only by a hidden system of technology. They underlie every step and every action. And in each step, you'll begin to learn some of the history behind it and how we live in one large technological web that is created by engineers. And what I'm going to be showing you is what I see as I go through a typical part of my day. So I'm going to spend the next 45 minutes telling you the stories behind that hidden world that surrounds me. So let's, do we need to lower the lights at all, I guess? So let's just start very quickly with what my day is like. All right, 6:59 a.m., 7 a.m. All right, the alarm clock goes off. Notice the alarm clock back there. I walk to my bathroom. I look like I'm going to be sick, don't I? I mean, this is, I am not a morning person here, apparently. I go ahead and brush my teeth. You can see that I'm going to need to shave. I do that. And then I go ahead and shower. Now, there are many interesting things and engineering things that happen in the shower. There is soaps, and there is drainage, and there is water supply. We're going to skip all of that. There'll be no more shower pictures after this one. You're welcome. Then I walk down my steps to go to breakfast. You'll notice right there my suitcase. I travel so much that it's actually almost out permanently. In the kitchen, I like to make breakfast. In this case, I'm going to make a little bit of toast with a toaster, and I'm going to heat some tea in my microwave oven. Now, as I eat breakfast, I multitask a bit. I like to watch a little bit of television, catch up on news. I have a stack of magazines, and I like to browse through them a little bit. After breakfast, about 7:35, I pack a lunch. putting it in here in the plastic container. And then I head out the door. And actually, I don't make it out the door here at 7:40. At 7:41, my wife, Amy, points out that I should take the trash out. So I do make it out the door, but in this case with a bag of trash. And then onto my bicycle. I don't know why I look like this here. I guess it is 7:45. Here's a little better picture. I'm heading off to work. It takes me 4 minutes and 30 seconds to make it to work. So this is the first 45 minutes, and right there I have highlighted the bag of trash that I set out earlier. So here's what I'm going to do. I'm going to share with you 12 very brief stories over the next 45 minutes that tell the story behind this sequence of actions, this first 45 minutes of my day. So let's start with that alarm clock. The alarm clock rings, and that's really the first sign of how technology has become a very intimate part of our lives. By rising, I'm responding to the first mechanical system that removed humankind from nature's natural rhythms. Before clocks, you see, we only had sunrise and sunset, and now we have very orderly lives that are regimented by the clock. But as I'm going to discuss with you, the influence of the clock extends beyond or just organizing our days. It really seeded the Western European domination of the world, and I'm going to talk about that. Let's start with the clock, though. When I rise here, I'm actually paying homage to the most world-changing invention, I think, of the Western world, and it's a small device which is called an escapement. And I'm going to define what that is, but it's the device that gives the clock its tick-tock sound. But before we get to that, let's look at early clockmakers. Early clockmakers modeled their first clocks on nature. And the sun, for example, marked the time by moving through the sky. Anybody could see that. And so early timekeepers built sundials. And they used that to chart the progress of time minute by minute. Now, sundials, though, didn't work at night, obviously. And they weren't very portable. They couldn't be easily moved. The next model for time measurement was the flow of a river, a flow of water. You can look at the river and you can see time pass. And so this is an example of a very elaborate Chinese water clock. And there's a wheel here that as the water flows down, this wheel spins and it fills up another reservoir and the level rises and they measured time. Now, both sundials, water clocks are very elegant ways to measure time, but they're very limited. Sundials, again, don't work at night. This isn't very portable, neither is a sundial, and you certainly can't use this in cold climates at all. And although ingenious, the real solution to measuring time, where these erred, was they tried to measure time as something continuous and flowing. And what they needed to do to make time go portable and to affect our whole life, to be independent of nature, independent of the elements, was they needed to not have a smooth, continuous motion, but regular, precise beats, and that was the key. In about the 13th century, some anonymous genius figured out how to turn the continuous unwinding of a spring or the falling of a weight or the movement of a pendulum into a regular burst that moves the hand of a clock. And this is the escapement that I mentioned. And you can see this wheel here, which is tied to a spring. The wheel moves in this direction. This escapement, which you can think like a seesaw, drops down. It stops the wheel, kicks it back in the other direction. It's stopped and then moves forward. So it does continually make a turn around, but it rocks back and forth and then turns. All right? Now, this, by alternately letting that gear go and by cutting up the spring, because if without this wheel would just rotate continuously with the spring, it would continuously accelerate and wouldn't keep time. But this escapement gives the clock its tick-tock sound, cuts the motion of that continuous unwinding of the spring into these regular beats, and really gave us an endless series of uniform motions that let us capture time. And it caused an explosion in timekeeping and ultimately a revolution in how we live. By the 18th century, the Western world was producing 400,000 mechanical clocks a year. And what they did was they allowed our lives to have a shape and to have a form that was independent of the sun and the moon and the movement of the planets. And it revolutionized our lives. One historian has said, It was the clock, not the steam engine, that is the key of the modern industrial age. Now, there's more from the clock in the sense that what it did was it laid the basis for the Western world to emphasize numbers. In the 9th century, Central Europe really trailed under other regions. The Muslims, for example, excelled in mathematics and mechanical innovations. The Chinese also in mechanical innovations. Yet, from about the 17th century on, Europe dominated the world. And there's no better example of that than Queen Victoria. You can compare her to Alexander the Great or Genghis Khan. They each held a continent and at times a wedge of another, yet they were homebodies compared here to Queen Victoria, on whose empire the sun truly never set. And this is an editorial cartoon. This is Queen Victoria. This is her Prime Minister Disraeli, and he's giving her the crown of India. Now, it's not only true of Queen Victoria, but other European empires at various times, France, Spain, Portugal, the Netherlands, and Germany. They all controlled large sections of the world. So the question is, between the 9th century and the 16th centuries, what exactly was it that happened? How did these bumpkins, and that's a fair description of Western Europe in the 9th century, how did they manage all that? And the answer is something that really warms my engineer's heart. The answer is numbers, or better put, quantifying the world by numbers. And let me explain what I mean by that. What the West did was they brought together mathematics and measurement to record reality. And that gave them the power to control it. We looked at the clock. That was the first quantification of the world. The early uses were in monasteries, where St. Benedict divided the working day into 3 portions. 5 to 6 hours for prayer, 5 hours for manual work, 4 hours for reading the scripture. And they used at first the chimes of a clock, of the church tower, and then they moved to clocks actually to regulate this. And then this quantification spread from the monasteries to towns. In fact, the chime of the town clock would divide the day into segments. It would tell you when to start the day, when to stop the day, when to trade, when to go to church. And it began to spread in other ways. Music became controlled by the clock. You can actually monitor the change from free-form Gregorian chants to music with a very rich meter. And oddly, very rich metered music led to regiments and to powerful armies. I want to quote Machiavelli here. He said, "Just as a dancing man keeps time with the music and cannot make a false step, so an army that properly observes the beat of the drums cannot easily be disordered." And this quantification began to spread to other aspects of life, and many of them are illustrated here. Paintings from the 9th century, and this is a little bit later, but these kind of paintings, they look odd to our eye. They seem flat. They seem lifeless. But the rise of measurement and numbers gave artists the power to put perspective in their drawings, to give them a realistic or at least a geometrically accurate look. And with accurate paintings evolved maps with grid lines. And you can see some mapping elements here laying out where various things are. And these lines, of course, guided sailors that moved across the seas to new worlds. And then the numbers let them control the worlds that they saw. This doesn't sound exciting, but numbers led to something called double entry bookkeeping. It doesn't sound like a world-changing event, but what it allowed was a merchant to picture, if you will, the reality of his or her business, and it let Renaissance Europeans control commerce, industry, and government bureaucracies. And I guess here the message is you should listen in math class. The poet Auden summed up these results for all these numbers for the West, and he wrote, "We live in societies to which the study of numbers, and that can be weighed and measured, is a consuming love." Now, I have to say here, when my alarm clock goes off, I usually don't have any feeling of consuming love, and I rise, but I don't really feel like conquering the world at all. And in fact, I head right into the bathroom here and stumble into it. So let's look at this section of the day. I'm in the bathroom. I'm in a thicket of technological systems here, of electricity, of plumbing, of sewage. And all these are very rich with complexity. They all compare to the systems that brought about this, a razor. And very specifically, the razor that you're looking at here. It doesn't look like much. It looks like a bit of plastic and metal. And yet, the 3 blades that are in this, I have a close-up here. This is a 3-blade razor. There's ones made for both men and for women. And this is truly a tour de force of engineering that you're looking at here. The development and the design cost $750 million for this razor. Now, let me tell you the story of this razor. For a long time, razors used only 2 blades. But manufacturers had the quest for this holy grail of a 3-bladed razor. And the reason they wanted it is it cuts more hair without irritating the skin. And that sounds very simple. You just add a 3rd blade. But it's really very high tech. So here are the 5 steps that were taken to develop this razor. Step number 1. They had to understand shaving. An engineer developed a very high-powered microscope. He used it to magnify a freshly shaved chin about 40 times. And peering through the microscope, they developed a laser-guided device to measure how much hair was cut by each stroke of the razor. In step 2, he passed this information of what happens with a razor on to a colleague who wrote down a set of equations. They're called finite elements. And what he did was he modeled scientifically shaving in a computer. And what this computer model let other engineers do then was to study shaving before designing a new razor. And here's what they learned. They learned that as a razor moves down the skin, it makes the skin bulge. It forces the hair up and out. The first blade catches a hair, pulls it up, and slices through it, after which the hair starts to retract. And they saw that the second blade cut the hair before it could fully retract and trimmed it a little more. Now, there's a basic understanding. They could see that a 3rd blade would cut even more hair, that it would cut 40% more hair. They were very precise about it. But they learned from their computer simulation that the 3rd blade would get too close to the skin, and it would tear the skin slightly. But as I said, for razor manufacturers, the 3-bladed razor was the holy grail. And so they used their computer model to make the 3rd blade work. They learned that if they tipped that blade slightly at an angle to the other 2, it would cut the hair but not significantly cut the skin. But then they faced a problem. How do you pack all 3 blades in here? They found out they didn't have room for them. So that goes to step 3. They tried first to make the blades thinner, but they became too fragile. In fact, they reached the point where when a hair would actually break or blunt the blade. So another engineer entered, this time a metallurgical engineer, a specialist in metal. And he realized you could cover the steel blade with a thin layer of something very hard. And in this case, he used a thin layer of carbon that makes a diamond-like coating on the blade. So now they have a razor with 3 blades. They're stronger than steel because they're coated, and they cut hair better than anything else. The 4th step, which is one we can't neglect, and I'll come back to it and a number of other things today, is consumer appeal. In the case of this razor, which is an Edge, I think an Edge 2, the marketing team decided to ask their engineers to examine Arnold Schwarzenegger's movie Terminator 2 and match the finish on the razor's handle to the movie's liquid metal villain to give it a mercury-like finish. And then step 5, you have to make the razor, and they had to build what was called a Class 5000 clean room. A clean room is more pure and cleaner than any surgery ward in the world. In fact, it's where semiconductors are made. And in that facility, there's white-coated workers that carefully coat the blades with this diamond-like carbon. So, $750 million worth of stuff to make a simple razor that you buy only for a few dollars. I'd like to note we're only at the bathroom, and we've covered now the history of Western world from Roman times to today. And we've uncovered the necessity of a multi-billion-dollar high-tech clean room. So let's continue. The next thing I want to look at is brushing my teeth. And actually, we don't want to look at that. Let me show you. I am one of those adults who has braces. And this arch wire right here is really an incredibly amazing thing. Here's a close-up of it, all right? This arch wire. And of course, it's a slender wire. It supplies the force that moves my teeth about 1 millimeter a month or so. And it withstands long-term assault in the body's harshest environment. Your mouth contains acids from food and from digestion. Biting and chewing is very much like a jackhammer. Toothpaste and brushing is highly abrasive to the wire, and yet it lasts through all this. And yet nothing of what I've said is what makes it truly special. Here's what's amazing about it. This wire has a memory, and it can be bent, and then when heated will return to its original shape. The wire, which is called nitinol, began life in 1958 with a man named William Buehler, a metallurgist at the US Naval Ordnance Lab. And he was actually searching for a metal for missile nose cones. And he wanted one that could withstand the forces and the heat of reentry. And so what he did was he tested various alloys. Alloys are a mixture of different metals. And he noticed that an alloy that was made from nickel and titanium behaved very differently from the others. And he demonstrated it at a lab meeting in 1961. And I've brought a picture of this kind of behavior. This is an antenna that is used on a spacecraft. I think it's used on a spacecraft, yeah, with solar heat. And it balls up, but when heated by the sun, it actually unfolds by itself to this large cage-like structure. And in the case of the Naval Ordnance Lab, his assistant actually brought out a strip of the alloy folded like an accordion. He was a pipe smoker, and he lit a lighter, and everyone watched it unfold and were amazed by it. And this was named, the name nitinol comes from Ni for nickel, Ti for titanium, and NOL for Naval Ordnance Lab. Now it works because the atoms in the metal rearrange into what's called a new phase. We usually think of a phase change as something dramatic. An ice cube melts, changing phase to a liquid. We put water to boil on the stove, and it changes from a liquid to vapor. But less well known is that such changes occur within solids. You can have a rearrangement of the solids, which is a solid to solid phase transition. And in the case of nitinol, it remembers its shape above a certain temperature. Now, there are thousands of uses for this alloy. I want to mention some of the more interesting ones. There are greenhouses where when the temperature inside gets too high, they have hinges made from nitinol so the windows actually open. In the case of my teeth, the nitinol wire, the dentist can actually shape it with his hands. Then when it's put in my mouth warms it up, and it retains its, it snaps back into shape. There's some more exotic uses. You can actually buy a shirt woven from nylon fibers with nitinol wires interspersed. And when it gets, when your body temperature rises too high, the sleeves actually automatically get shorter. It costs about $4,000 or so. I don't know how many they sold. Here's a more serious use for it. This is called a nitinol occluder. There is something called an atrial septal defect, where there's a hole in the heart that allows the two chambers to connect. And they're actually able to have a nitinol occluder, which is a plug for the hole, which they put in, and then use that changing shape property to fill the hole and to snap into place. That's probably enough on nitinol, but here's one more that I think is quite interesting. You used to be able to buy a spoon that was made of nitinol, and when somebody put it in their coffee, it would bend. And then you could take it back out. And I'm reminded of a quote from the science fiction writer Arthur C. Clarke, who wrote 2001. He said, "Any sufficiently advanced technology is indistinguishable from magic." All right, next on to the kitchen. And here in the kitchen, I like to make toast in the morning. And we've all heard the phrase, "It's the best thing since sliced bread." But was sliced bread really such a great thing? The answer is yes. Sliced bread was the culmination of a century of technological innovation. All sorts of things had, in case you don't know what sliced bread looks like, I brought this picture along. I don't know. Let me start with the end of the story and work backwards a little bit to show you what kind of technological things had to happen to get sliced bread. The end of the story starts with an Iowa jeweler and peddler named Otto F. Rohwedder. He preferred just to be called Roe. And at the beginning of the 20th century, toasters were in vogue. And Rowe often heard in his sales calls to grocers that people liked toasted bread, but they found it difficult to slice so it would fit into the slots. So the toaster represents the crest of one wave of technological innovation that brought us sliced bread. It began with a huge effort to electrify the nation. This is a satellite image of the United States at night, and it gives you a very good idea of how extensive the electrical power grid is. And I think we're right about here. I actually fly so much I forget to look, and I get dizzy looking out the window, but I guess we're right in here somewhere, right? And am I too high? Okay, right down here? Okay. I apologize. The planes defeat my geography. You get in the plane, it gets you there. If it doesn't get you there, it didn't matter what the geography was, right? And once homes were wired, this created a huge demand for household appliances, one of which was the toaster. So you have the electrical power grid, you have the toaster, and it creates the demand for sliced bread. Now, propelled by the demands of the toaster, Rowe built his first bread slicing machine in Illinois, not far from where I live. And a baker in St. Louis, Gustav Papendick, brought the second slicer produced by Rowetter, and he improved the cutting action, but he found out that bakers objected to the sliced bread. They felt the loaf would dry out too quickly. And so Papendick invented a machine that would wrap the bread to keep it fresh. And to do this, he needed to keep the sliced bread together long enough so his machine could wrap it. And he first tried rubber bands and then metal pins to keep the loaf intact, and both failed. And finally, he just came up with a simple idea. He developed a little cardboard collapsible tray. He put the bread in it, and that would precisely align the slices so the machine could wrap them. Now, it sounds simple, but again, a series of technological innovations to make that happen. If you're going to have uniform bread trays and a bread slicing machine, you need to have uniform bread. So this is non-uniform bread, as you can see. You can't slice this. What happened to give us uniform bread? A whole slew of things. Some engineering genius invented the automated flour mill, and then you could make large quantities of bread. And then a technology evolved for making identical loaves of bread. One of the things that had to happen was ovens. This is an oven from 1910. Early ovens used embers. They cooked the bread slowly and evenly, giving the kind of loaf that we saw before. And then industrial ovens came along, which blew an even stream of hot air past the dough. And in addition, they were continuous, and there's a belt that dragged the bread through here. And because this is very long, you can have a large section in here that is heated and heated evenly. So dough went in one end, and out came mass-produced uniform bread on the other end, which could then be sliced automatically. You still had the problem of the loaf drying out, and eventually that was saved by another innovation, which is plastic, which made a moisture-proof wrapper that you could wrap the bread into. So all of these innovations came together, and in fact, when Gustav Papendick in St. Louis introduced sliced bread, he increased the sales by some 80%. And he gave rise to that phrase, the best thing since sliced bread. Well, let's move to another section of the day. I like to heat my tea in the microwave oven. I like to use it because it heats very fast. But very oddly, the oven nearly failed to catch on because at first it heated too fast. And the microwave oven is well over 50 years old. The first one appeared in 1946. It was a direct descendant of World War II military technology. And a company called Raytheon produced radars for the US Armed Forces. And the heart of a radar and the heart of a microwave oven is a vacuum tube called a magnetron, which is shown here, and this is another one over here. We think of the vacuum tube as being completely gone and everything is replaced by digital circuits and chips and things, but it turns out the vacuum tube is very much alive. Every one of your homes, if you have a microwave, has a large vacuum tube inside it. What a vacuum tube does is it produces high-frequency radio waves that are absorbed by fat and water. They make the water molecule spin, and that generates heat. The engineers at Raytheon noticed this first because of the cold Boston winters, they would build these radar tubes, or magnetrons for radars. They would put them in metal racks on the open. They would plug all of them in. They were running the microwaves, the vacuum tubes, in order to be sure that they seal and to test them. And they noticed as they walked in the door that these things were giving out heat, and they would actually warm their hands under the radar tubes. Well, after World War II, Raytheon no longer sold as many radars. They decided to do something commercial, and they built a microwave oven. This is Raytheon's first commercial microwave oven, built in 1946. I took this picture at the Raytheon archives. I am the world's expert on the history of the microwave oven, which hasn't got me very far, but it's an interesting thing nonetheless. This oven is 62 inches tall, so a little over 5 feet. It weighs 670 pounds. It's 2 feet in depth. And not only did it take up floor space, it required a team to install it. An electrician had to put in a 220-volt line. That, of course, is what you use for a washer and a dryer. And a plumber had to install a water line to cool the oven's radar tube. And this oven sold for $2,000 in 1946, which would be, as I calculate it, $17,500 in today's dollars. Now, it was a very powerful machine. You could cook a 6-pound roast in 2 minutes and a hamburger in 25 seconds. And let me explain what's going on. We think of engineers as being these analytical people that just design things precisely. It turns out the people who designed this had just come off of World War II production, where they had to make so many radars and had to be so efficient at making them, otherwise lives were lost, that all they could focus on was efficiency. So the faster that oven cooked, the better it must be. And we're going to find out that that wasn't necessarily true. In fact, they took 20 years to try to sell it, going through various forms, and it failed always to take off from about 46 to 66. And then in the mid-1960s, they acquired Hammack Corporation. Hammack Corporation was a maker of consumer refrigerators. And when they got a hold of the oven, the first thing they did was they redesigned it by slowing it down. They said, look, fast is, 60 seconds to cook something is fast enough. You don't need 5 seconds or 15 seconds. They made it so it used a standard plug. Cooking slower, it didn't need as much power. And they also made it so that the magnetron didn't require water cooling anymore. Now, to be fair, they, in slowing it down, were reflecting different habits and a different social structure from the oven's debut in 1946. When they introduced the microwave, it was a time when they thought it would replace the oven. They intended to cook whole roasts and to cook lobsters, and the patent even describes cooking, quote, thick bodies of meat. Now, a microwave cooks meat actually rather poorly, or actually protein rather poorly, and by the mid-1960s, there was a faster pace of life, often from two parents that were working, and it resulted in more packaged food, usually had smaller amounts of protein. So in the new household of the early 1970s, the oven actually thrived as a reheater rather than a substitute for a conventional oven. And Hammack advertised these with the slogan, "The greatest discovery since fire." And 1978, they sold just behind, in 5th place behind refrigerators, washers, dishwashers, air conditioners. By 1985, it was the #1 best-selling appliance. Now, the next thing I want to look at is inside that microwave. Oh, I'm sorry, I hit that. I want to look at the tea. Actually, I don't want to look at the tea at all. I want to look at what I put in the tea. And actually, I don't want to look at what I put in the tea. I want to look in what's in the refrigerator. Now, I have been looking at all these things that affected my life, and I want to take a moment to look at something that is surrounding me that is unnoticed at all. And as I open the fridge here, you can see a 2-liter soda bottle. You can see 2 of these. And that 2-liter soda bottle really illustrates an essential truth about engineering, and that is a creative act. And I want to show you what I think about, truly what I think about every time I see a 2-liter soda bottle. This is Christina's World. It is an enormously famous painting by Andrew Wyeth. It is an American masterpiece. It is well known for extremely graceful lines and also for being having a simplicity to it. The plastic bottle and this painting are closely linked in their simplicity and in their lines, in a sense, because this was painted by Andrew Wyeth and the plastic bottle was invented by his brother Nat Wyeth. Now, they were both influenced by their father. Their father was a great illustrator. He would illustrate. I remember seeing a painting of somebody plowing a field, and you can just almost feel the muscle strain in the way that he used the details. And he taught both of his children this idea of design, of simplicity. In fact, Andrew recalls that he was painting one day, and his father walked in and said, "Look, you've lost your simplicity." And he took out his thumb and he simplified a shadow. And as Andrew said, he made it sing. He made the painting sing. And that simple detail brought the painting to life. Now, Andrew's brother Nat also spent his childhood learning simple details from his father. And of course, the result is in the museums or galleries. It is in your refrigerator. And when he told his father, who was a painter, and in fact had come from a family of painters, that he was going to be an engineer, his father said, "An engineer is just as much an artist as a painter." So here's the story of that bottle. In the 1960s, Nat Wyeth created his masterpiece by asking himself, why isn't plastic used for soda bottles? And he went home, and he went to his basement and got out a plastic bottle used for detergent, took the top off, emptied it out, filled it with carbonated soda, put the top on, and put it in his refrigerator. Then the next morning when he got up, he found it wedged inside. He found it wedged inside his refrigerator because the carbonation had caused the bottle to expand. And he realized that the plastic used in a normal bottle was much too weak to contain the pressure from the carbonated soda. And he realized that what he needed to do was to take the long plastic molecules and actually weave them together a little bit like a net. You think of a net and it can hold things. And a net of plastic could hold the pressure from the CO2. The problem was how to do this on the tiny scale of molecules. And I'm about to get kicked out of the Jefferson science lab here, but he made a mistake for an engineer. He went to a scientist. And they paid for my plane ticket already. So the scientist said, and I quote him, "You have as much chance as balancing a steel ball on the end of a needle." And Wyeth, though, succeeded by using the simplicity he used from his father. And I want to explain how one of these bottles, very briefly, one aspect of it is made. This, of course, is the full bottle. This is a blank. This is a thick piece of plastic, but it contains all the plastics here. And what Wyeth did was he lowered this into a mold that was shaped like the plastic bottle. He heated up the plastic until it became molten or nearly flexible. And then, and here's the simplicity, he just simply shot a burst of air through there, and it caused the plastic to splatter all over the side of the mold, creating this chaos and weaving these molecules together and creating the plastic bottle. Now, as I said, this is a very simple design, and to my eye, at least very beautiful, and I do truly see the painting Christina's World when I look at this. Well, I want to now look at something else while I eat breakfast, and I'm going to skip one slide here. It's a picture of the person who invented TV. He was 19 years old when he did it, and it is a separate story, but I want to go by it quickly there. I want to look at the color pictures that we see here. And in the morning, as I mentioned, I often multitask, and I glance through magazines and I look at pictures. And I want to focus here on the color pictures, both on the set and in the magazine. And they reveal something very, very important about technology and about engineering. Now, in a sense here, I've been celebrating the achievements of engineers, at least implicitly. And I don't want to make out technology to be what I'll call value neutral or culturally neutral. Any technological breakthrough is not culturally neutral. In fact, all technical objects reflect in some ways the values, the worldviews, the intelligences, the stupidity, the biases, the vested interest of those who design it. You can't separate it from the social and cultural context. And I'm going to give you an example right now. If you look at this magazine here, you can see the cultural bias when you look at the color pictures. And the photograph on this page is to be a representation of reality, but it isn't that at all. The color film that was used to optimize to best reproduce was optimized to best reproduce Caucasian skin tones. And I want to explain how that came about. It came about because it's impossible to faithfully reproduce colors on film and to do it cheaply. And instead, engineers developed ways to use three colors. And you're probably very familiar with this. Red, yellow, and blue can be used to make colors. Here you put red and blue together to get parts of this flower. A deeper blue where the red and blue overlap. Where the blue and yellow overlap, so this comes together, these two, you get green, and you can mix and make the colors. And it would seem like this matches what goes on with the three cones of our eye, yet in reality those cones overlap with what it is they receive. So if you use the three colors to create white, the result is actually tinged with magenta. And you can restore full whiteness by fiddling with the mix of the three primary colors, but only at the cost of distorting all other colors. And so what they did to develop the color balance, when they developed film stocks, they used a series of prints of a young woman. This is actually a print from 1946, which was used to determine how well color film worked. They submitted these to judges, so they would vary the color. So they were 2 red, 2 yellow, 2 blue, 2 green, 2 pink. And they submitted these to judges who chose the best reproductions, and they rejected the print that matched the real colors in the woman's face and chose as best the prints where she was actually quite pale, and thus they optimized them for light Caucasian skin. In fact, other skin tones in the early days of television, of color television, they often came out with a greenish hue to them. Now, I'm not suggesting here that any kind of crude conspiracy, but I want to draw attention to the fact that an inventor's own cultural values do become embedded in technological objects. And so when you adopt a technology for a lab, for a library, you should be aware of these cultural constraints. Now, I want to talk a little more about the cultural aspects of technology in a way. I'm making lunch, and I'm putting it here in a plastic container. That is a real live piece of Tupperware from my mother-in-law. Actually has the Tupper Craft, which was one of their brands. I one time did this presentation, and I actually had a piece of Rubbermaid, and I had people yell at me when I called it Tupperware. So that is, you can see it, that's real Tupperware here. Now, the story leads me to illustrate another aspect of engineering, and that's its need to fit in the world. You see, we kind of had this image that you have a scientific breakthrough, and then of its own accord, it takes over the world and becomes part of it. And yet, what really has to happen is you have to look also at the social side of the object. Good engineering is a blend of these two things. And in fact, Tupperware containers became permanent cultural fixtures only through great engineering, which I'm going to discuss, and by tapping very deeply into the psyche of our culture. And I want to start with Earl S. Tupper. This is Earl S. Tupper. Here's a description from his biographer. Earl S. Tupper, a failed tree surgeon and archetypal reader of the Reader's Digest, who combined faith in technological progress with a Protestant conservative suspicion of bar-hopping men and cigarette-smoking women. Tupper was a very prolific inventor of bizarre gadgets. He invented the knee-action gypsy gun. You put it between your legs, you moved it back and forth, you shot gypsy moths out of the sky. He invented slip-proof garter hooks and shields for dyeing eyebrows, which he tested on his sisters. He invented something called the Tupper bomb, which discharged carbon dioxide on impact. He advertised it as useful for dispersing striking factory workers. And he did this in the 1930s. And he worked in the 1930s at DuPont. And he worked with a new plastic called polyethylene. And he was very frustrated there because his bosses could see only very simple military uses for this plastic. And as we've seen, Tupper had an inventive and oddball mind, to say the least. And here's what he saw. He saw something that was tough, that was flexible, that was non-toxic, that was odorless, and it was lightweight. So in about 1939, he tossed his bosses into selling him a few tons of the stuff cheaply. And then he spent every spare moment at his farm in a tiny Massachusetts town playing with the polyethylene to find a way to prepare it so it wouldn't crack when shaped into something. And this is his original patent. You can see the idea of burping Tupperware was actually in the 1949 patent. And he heated the plastic to make it pliable and moldable. The trick was to find just the right amount of heat so the plastic became like chewing gum and could then be slapped into shape, but not so much heat that the plastic melted. And after 3 years of trial and error, Tupper found the perfect hybrid of material and of technology and design to make plastic kitchenware. And this is his first. This is in a magazine called The Tobaccoist. And these are the first things he sold, which was just a set of simple tumblers. So Tupper had made the scientific breakthrough that allowed Tupperware to be made, but that wasn't enough to make it successful. To become part of our national culture, as Tupperware did in the 1950s, it had to tap deeply into our traditions and into our anxieties. Now, subliminally, he had some luck in that Tupperware was resonated with America a bit because you could use it in the 1950s to keep food in fallout shelters. But tapping much deeper into American traditions was beyond Tupper himself. So he hired someone called Brownie Wise, who had a very intuitive grasp of female popular culture, which is how Tupperware was first sold. Brownie Wise grew up in the South. She married at age 23 and lived there until the Depression hit the South, and then she headed with her husband to Detroit, where he found a job on the Ford assembly lines. And their marriage was very unhappy and very short-lived, and 3 years after the birth of their only child, they divorced. And to survive, Brownie Wise started selling something called Stanley Home Products. And the company employed housewives as saleswomen and encouraged them to push its wares through their social context. So Tupper hired Brownie Wise, this single mother from Detroit, to pioneer Tupperware's famous hostess parties, which were actually her idea. And you're familiar with these. You gather a dozen people in a house and demonstrate the housewares. And I just absolutely love this as a cultural piece. Tupperware are what dreams are made of. But here's what Brownie Wise did. She grafted the selling of Tupperware onto the American traditions of the sewing circle and the quilting bee. And she tapped into the psyche of a new suburban housewife. And the parties took advantage of a sense of isolation and a sense of social obligation that was common at the time. And a feminist called these parties a form of organizational parasitism analogous to colonialism, which used the existing tribal structure. And that might well be so, but Brownie Wise was enormously successful. And in 1954, Tupperware sales topped $54 million and made her the first woman ever to be on the cover of Businessweek magazine. And now today, there is a Tupperware party in the world every 2.2 seconds, so that means that in the 45 minutes or so that I'm talking to you, I guess there is some 1,000 to 1,200 that have just occurred in this time. So, history of Tupperware shows then that any technology produced by a scientific breakthrough must fit into our culture in order to be successful. So, I want to look here then at not this slide. This is actually Velcro, and I'm going to skip Velcro right now. I want to look at this last slide. Remember that instead of saying, in addition to saying goodbye, I should say, my wife reminded me to take out the trash, and it's an appropriate story to end on here. As an engineer, I like to dwell on designing and making stuff, the glamorous side of engineering, but there is also the dark side. Every product must be tossed out at some point. In fact, a trail of trash is the hallmark of human presence. We have found 2,000-year-old waste from Mayans, and the first time humankind left the Earth to go to the moon, we left our urine bags behind. I want to stay closer to home today. I'm going to give you not quite a guided tour of a trash dump. I'm going to ask the question, what typically is in this bag? So let's take a look. If I use this box to represent the volume of all trash produced in the United States, we want to begin to divide this box up into various pieces. And so you know that we live in a disposable fast food culture, and so I've drawn a box here that takes up some 60% We have trash from fast food and foil. Here's a foam container that a salad came in from the local grocery store. We have all sorts of other foam products that we use, and most people would say that fast food packaging, styrofoam, and the nasty diapers take up 60 to 70% of a landfill. So if this is all the trash in the US, this is the part taken up by fast food packaging. Let's look at what actually happens. There's fast food, 0.5%, all of the trash from fast food. And in fact, what I've added in here to get up to 1% is all of the foam containers that we use. Fast food containers, egg cartons, meat trays, coffee cups, peanuts for packing. It all adds up to 1% of a landfill. Let's take a look at diapers. The New York Times labeled them the premier symbol of our nation's garbage crisis, and in fact, nearly 90% of American babies are diapered with disposables. 2%. So if we add up diapers, foam containers, and packaging, what most people think up makes 70% of a landfill, what is actually taking up the space? Well, partly plastics, 15 to 16%. They take, but this percentage has actually been decreasing because manufacturers are able to make their products thinner. For example, that 2-liter soda bottle that I've shown you has dropped in weight by 30% over the last 3 decades. And that's a very simple economic reason. Less plastic in the bottle means lower costs mean greater profits. So where's the problem with landfills? It is paper. This accurately represents the part of landfills that is taken up by paper. Paper takes up 40% and is growing. A year's worth of the New York Times weighs 50 pounds and takes a volume equal to about 50,000 Big Mac containers. So think about it for a moment. If you read the New York Times every day, that's 50 pounds. You certainly don't eat 50,000 Big Macs as an individual in 1 year. Landfills are stuffed with paper used to make packaged goods, which has grown by 1/3 since 1960. There's paper plates, junk mail, and computer paper, which has all doubled over the decades. And in fact, the computer, the foundation of our paperless society, is at the root of our paper problem. So the point here is not that we don't have a garbage problem necessarily. That's an issue to discuss. But that it's different from what we expect based on our visits to fast food restaurants, on diapering our children, or tossing out plastic. And there's a lot of debate about the proper solutions for these. They range from mandates by the government to free market solutions. That's the whole gamut. And regardless, the real first step is to see what the exact problem is. So the end of my day, here I am on my bike on the way to work. And there is, of course, 45 more minutes to my day as I ride my bike to work and work at my office and maybe go to the airport and come out here. But you'll have to invite me back to see the next 45 minutes of my day. So thank you for listening. Wonderful.
Folks, we've got a few minutes for questions, and we want to try and get out of here 8 o'clock or shortly thereafter. Does anyone have any questions?
There are several ways to hear me. One, it is always available through the web. There is a regional distribution that I don't think makes it here. I appear on Marketplace from time to time, which plays here. And I'll be on Marketplace actually next week talking about potholes, of all things. And then if you go to Australia, you can hear me on the Radio National Network in Australia every week. But that's an expensive way to do it, I would imagine. Yes.
Yes, sir.
The new what? Oh, yes. I'm just simply outdated. But there's a huge competition to make razors, and here's the information I haven't been able to get about that razor. Is that razor a real technological innovation, or is it simply a marketing ploy where the fourth blade doesn't do anything? It turns out that razor technology is highly proprietary. And so I can only be about 10 years behind the time because they won't share with me what is actually going on. So it would be about 10 years before I understood the four-bladed razor. Yes.
Well, thank everyone for coming this evening.
Excellent.
If you have more questions, please step down to the front and speak with Bill directly.
Great.
Thanks again. Good night.
Thank you.
George, your comments, Dr. Hammack.
Thank you.
Very good.
Thank you. I appreciate it.
Champagne on banana?
Yes, that's correct. Yes. Okay, that's for you.
This is for me. Thank you.
Okay, thank you very much.
So see ya in the fall.